Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode, you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media.
There are a number of superlatives to meet in the quest to deliver the world's best AI supercomputer. To be the best, the device must also be the fastest and the safest, as well as the most accessible and the most practical. The race to the top of the mountain runs through Silicon Valley. That's where 4-year-old Luminous Computing operates. The company's designs on developing a supercomputer so powerful that current superhuman AI capabilities are far surpassed relies on a Silicon Photonics platform. Luminous recently named Silicon Photonics luminary Michael Hochberg president. Hochberg, an industry veteran who has guided 4 companies to successful exits, joins the efforts of company CEO Marcus Gomez. Gomez founded Luminous in 2018, and together the pair has its sights set on an optical solution to a bottleneck that has come to capture the attention of some of the brightest minds on the planet. As the company emerges from stealth with a new president and freshly announced $105 million in Series A funding, our quest on All Things Photonics is to understand how Silicon Photonics pushes the pace towards a complex supercomputer architecture and model capable of changing the world. With an explanation first from Gomez, and then a macro look at advanced computing from Hochberg, today's episode begins with a quantification of the impact of AI supercomputing and thoughts on what it will take to summit an increasingly solvable problem.
The question is, what is the bottleneck on building this useful, usable, safe artificial intelligence? And we spent sort of the past several years studying this. And what we found is that it's fundamentally a hardware problem. So at a basic level, the way these AI algorithms work is that they get better by getting bigger. And so 10 years ago, the largest model you would have seen in the literature was only 10 to 50 million parameters, which sounds big, but it's not. You could fit it on a GPU. You could probably train it in a couple hours. You could deploy it instantaneously. Today, the biggest models in the literature are on order 10 trillion parameters. They take up to a year to train across tens of thousands, if not hundreds of thousands of machines. And therein lies the problem, because when you're talking about a year to run an experiment, you're hitting the tractable limit of how long a human could keep track of an experiment. You're running out of space in the data center. You're running out of power in the data center. It's becoming cost prohibitive. Not to mention, you're throwing millions and millions of dollars into software engineering to eke out the last bits of performance. And hardware just hasn't kept up. And so what we're doing at Luminous to build that artificial intelligence, we're starting by actually building the computer that's actually efficient enough to run these giant algorithms.
There's sort of a tautological situation in the industry right now, which is the algorithms that are commercially important are by definition the algorithms that run on today's hardware, right? So it's not a question of one thing running out ahead of the other. What's really interesting to me is that, normally when you go to software people or to algorithms people and you say, well, what's the solution to this? They say, well, Moore's law gives us, improved computers every generation. And fundamentally, this is a software problem because they're software people, right? In this case, what's fascinating is the level of customer pull, which is we go and talk to people who are, fundamentally software people. And what they describe is the incredible difficulty of getting these large models onto these big clusters, huge teams, huge amounts of effort. And at the end of the day, what we're solving is not just bringing new capability to run large models, but it's doing it with a piece of hardware that makes it very easy to do that with a small team.
Let's talk about some of the trends, some of the recent developments, specifically in the domain of silicon photonics. And this is for one or both of you. Can you outline, and I suppose broad strokes would be the way to go here, the plan of attack to hasten development of the necessary hardware components?
I guess the way I would frame this is that there have been really 3 eras of silicon photonics. The first one was in the 2000s when it was a big struggle to get silicon photonics inserted into any socket, right? You had to use existing sockets you had to play into existing sockets because no one was willing to bet their supercomputer or their data center or their end application on silicon photonics because it was an emergent technology. It was something that was perceived as being very risky. Then you had this transitional decade from 2010 to about 2020, when over the course of time, silicon photonics came to dominate every transceiver socket there is in the data center and in the metro and long haul world. So you go into a modern metro deployment, and chances are you're going to see either mostly silicon photonics or all silicon photonics. Same thing with DCI, same thing with long haul, same thing with the connections within a data center at 400G, right? So silicon photonics became, in many ways, the default technology for new transceivers. And the wider industry got comfortable with the idea of making bets on silicon photonics because it got to the point where, with a reasonable sized team and the right tools and the right funding, you could tape things out and have them come back working in one or two spins through the fab. So now what's going on is that it's possible to plausibly bet an entire system, something that's a system level innovation, on something that can only be delivered in silicon photonics. And the thing that silicon photonics gives you that no other photonic platform lets you do is to rapidly scale complexity. And that's what we're doing, right? We're building what are going to be the world's most complex silicon photonic chips in order to radically alter the economics and the dynamics associated with moving data around within the supercomputer, and let us address some of the fundamental architectural challenges that have plagued computing for the last 40 years.
So you touch on a number of, themes there. There's this issue of scalability that you've addressed, cost and accessibility you've touched on, ease of operation, usability. When you find yourself explaining this to not just our audience, but to anyone ranging from coworkers to investors, the whole gamut, what do you say? What are some of the common questions that you often find yourselves addressing, whether they're doubts or whether they're areas of confusion? Are there any principal confusion areas, I guess is a better way of framing this question, that you often find yourself having to address?
What's interesting is there's both interesting questions that get asked, and there's also interesting questions that you'd be surprised that don't get asked. So the thing that almost never gets asked is this a lucrative opportunity? I actually, over the course of, I guess this company has been around for almost 4 years, I've maybe been asked total addressable market once or twice, which is surprising for a venture-backed startup. And the reason for this is that it's actually it's so obvious to everyone who's looking at this space and everyone who's looking at AI supercomputing that the company that figures out how to build AI hardware that powers the next 2 decades of AI algorithms isn't just going to be another DoorDash or Uber-sized opportunity. It's going to be the next semiconductor titan. I mean, to give you a sense of this, right? Like NVIDIA just this year alone is projected to do something like $10 to $20 billion in just AI data center sales. That's not the total annual revenue opportunity. That's not, the total addressable market in 5 years. That's just what NVIDIA is doing this year in the data center for artificial intelligence. By 2026, that's supposed to be, projections are, depending on which analyst you talk to, somewhere in the order of $50 to $70 billion in an annual recurring revenue opportunity. And we think that's an underestimate. And again, this isn't surprising because the way that these models get better is by getting bigger. The way they get, they're capable of doing more complex things. The way they go from being able to do simple tasks to doing complex tasks, and the way they get better on existing tasks is by getting bigger, which means more compute, more memory, and fundamentally more bandwidth are required. In terms of the number one thing that does get asked, is silicon photonics actually far enough along and mature enough and cheap enough and manufacturable enough that you can actually realize this promised land? That bringing folks like Mike on board, I think, is honestly the strongest signal of whether or not that's possible, since he's been on the forefront of bleeding edge silicon photonics for the past 2 decades.
Yeah, let's touch on that because, Michael, you are new to the presidency here with Luminous. I want to ask you about the intersection of silicon photonics technology and Luminous as a company. Where did the two come together for you? What drew you to the position?
The founders here, Marcus and Mitch both, are just incredibly bright and their hearts are in the right place. What I mean by that is when you have very new founders who haven't done this stuff before, one of the things that you can see very quickly is, do they really care about the team? Do they really care about doing the right things for the people and in terms of the project? And, these guys really do. And that's something that is super important to me, especially because we're building stuff that has very large consequences in terms of how it's deployed and who it's sold to and all of those sorts of things. And so it's really important to me to work with a group of people who are thinking very carefully and in a very forward-looking way about the ethics of building this stuff and about who the right hands are to put this stuff into. These are potentially very, very dangerous capabilities that are being built. The second thing is that I really respected the pragmatism that I saw on this team. What I mean by that is, often when you have a company that started around, a founder's PhD work, which was the original vision here at Luminous. At that time, it was really focused on optical compute. When that vision it's frequently the case that vision doesn't survive the test of looking at a commercial project, right? And in this case, what happened was that the optical compute thing, when they looked at it really closely and they did the architectural studies and they thought about it and they talked to customers, they came to the conclusion that it didn't solve a sufficiently impactful problem. And then they pivoted into doing something that was incredibly impactful. That's a hard thing to do in multiple dimensions. And the fact that they did that and that they pulled it off and that they executed on that and they did it crisply and well was something that showed me that this was a place that was going to really execute on doing what needed to be done to build a product.
Before Hochberg's arrival and the aforementioned $100 million plus Series A funding round with investment from the likes of Bill Gates, there was a critical realization. Algorithmic advances alone didn't address the critical first wave of bottlenecks Luminous remains committed to overcoming as part of its greater solution. Breakdowns in the datacom and, even more plainly, fundamental communication were preempting the challenges of high-level compute. So, as Gomez explains, Luminous pivoted.
What we discovered at a very basic level is that doing the computation portion of these algorithms is simply not where the bottleneck is. If you look at the first 10 bottlenecks in these systems, they're actually all fundamentally communication bottlenecks. You don't get bottlenecked on compute until you've solved all of the communication bottlenecks. And so in net, what you have is, first of all, you're not solving a core problem for the customer because they don't really realize too much benefit from this. In exchange, what do you trade off to get marginal performance improvements? Well, you go from digital hardware, which is deterministic and high precision, and you transfer down to low precision, non-deterministic, noisy hardware. And the number one problem, besides the algorithms not going fast, not running fast enough on existing hardware, the other problem that our customers face is that these systems are, as is, just with digital hardware, are extraordinarily hard to use. And so you can imagine, okay, we take something that was already hard to use when it was deterministic, and we add a huge amount of randomness to the equation. We take away a huge amount of your precision from the equation in exchange for a nearly unnoticeable improvement in performance. It's just a non-starter. The number one problem that all of these software engineers are dealing with is they're fighting around the fact that they have really, really poor bandwidth at every level of the computer architecture hierarchy. So by solving the communication problem, not only do we deliver these order of magnitude improvements in performance, we also drastically simplify the programming model. We take things that used to take 40 or 50 engineers, and we reduce it down to problems that a single machine learning scientist can figure out on their own. And so we've gone from, something that, I regard as like a very important science experiment, and we've transformed it into something that is actually solving the number one critical needs for our core customers.
One of the realities here that I think is important to point out, maybe it's something that distinguishes, I'm not quite sure. But in any event, Michael, in addition to your optics and photonics achievements being quite deep, they're also fairly diverse, right? You've spent a number of years in the optics and photonics industry. I don't want to pigeonhole you into integrated or silicon photonics. Is there room here for you to deploy some of that knowledge in your new position for the benefit of what Marcus just outlined, these ambitious yet achievable goals?
Oh, yeah. I mean, you can pigeonhole me as a silicon photonics guy. That's fair enough.
It's been done before, yeah.
I mean, I do have other interests, but I would say that's the place where what I've done has been most impactful. I guess what I would say is that the reason that silicon photonics has been an exciting field at its core has been a march to complexity, right? And it's been a rapid exponential march to complexity over time. I published a paper, God, it must have been back in 2011 or 2012, showing on the basis of about 2 or 3 data points that there was a doubling time of, my recollection is that it was about a year at the time in terms of the complexity of the most complex published chips. Nowadays, people publish these roadmaps regularly where they show what's the doubling time for silicon photonics, what's the doubling time for hybrid integration, et cetera, et cetera. So, but like when we got started on silicon photonics, at Simulant and then at Luxtera, it was a seriously controversial thing to argue that the way that photonics was going to evolve was through a march to complexity. A lot of very smart people were utterly convinced that the way in which you should be innovating is at the device level by making better individual devices. And that's a trend that's continued in much the same way that people continue to make better and better vacuum tubes. Today's vacuum tubes are fantastic. There are things you can do with vacuum tubes that you just can't do with integrated transistors. But there's a lot of things you can do with integrated transistors that you can't do with vacuum tubes. And so everything that I have done that has been commercially impactful, and most of the things that I've done that have been academically impactful, have centered around the idea of figuring out ways to make use of cheap complexity to either do things better that people were already doing or to do new things that couldn't be done before because they required complexity. And that's touched a bunch of different fields, not just transceivers, but things like LiDAR and biosensing and quantum optics and the all optical compute stuff. It's touched a lot of different areas. The way I look at it is that what we are doing is in many ways the next logical step for the field, which is re-architecting computers around the idea that communication over medium and long distances can be extremely cheap. And that it doesn't have to be that the further you go from the CPU or the further you go from the GPU, the more expensive it is in terms of power and area and density to actually move those signals. I mean, that's what optics gives you. And what it does is it changes some basics about how you architect a computer. And that's something you can't get by building a computer and then attaching the optics later. You have to put the optics right at the center of the engineering effort, and you have to build the whole system.
As Luminous climbs the mountain, the phrasing, a march to complexity, has come to define the race that Gomez and Hochberg have entered in tandem. The contrast between the speed at which the world's best AI supercomputer is poised to operate and the time it takes to architect a device to arrive at that point only exists in our minds. There's a fast-moving pursuit here, and that is part of the appeal for Hochberg as he moves into his new role.
One of the reasons that I'm here and that I was attracted to this project is because this is an opportunity to go very fast. We are building a company that is designed to go very fast and to enable very bright, very independent people to work together as a team to go very fast. And one of the ways you see that is that we're actually building our pilot line right in our own facility, right? We're going to do as much as we can vertically integrated so that we can spin fast and get things out of the line and into the engineering team's hands and into customers' hands as fast as humanly possible. And, that's both for reasons of time to market, but also for reasons of safety. We want to be in control of the manufacturing pipeline for this, and we want to do it here in the US.
Today's episode is sponsored by COMSOL, the leading developer of multiphysics simulation software, which includes tools for building and deploying simulation apps. COMSOL's wave and ray optics capabilities are used for modeling, imaging, and sensing in consumer electronics and biotechnology, information processing and communication systems, and more. See how the COMSOL software fits your optical analysis needs at www.comsol.com.
It's time for the Luminary Minute, a segment where Photonics Media looks back at a pivotal figure in the history of optical and photonic science. Martin Pope, a physical chemist and professor at New York University, recently passed away at the age of 103. Pope, the son of Jewish immigrants from Ukraine, is perhaps best known for his research in the fields of organic insulators and semiconductors, and his discoveries of ohmic contacts. That work led to the development of organic light-emitting diodes, as well as developments in electrophotography, photovoltaics, biosensors, and batteries, among others. Pope sought to develop a more malleable alternative to silicon semiconductors for easier fabrication of thin films used in electronics. His experiments focused on anthracene and tetracene, which he found to have the necessary properties to act as an analog to silicon. Published in 1963, his paper Electroluminescence in Organic Crystals showed that electricity could be deployed to generate light in anthracene. The paper has seen more than 700 citations. Pope's work also extended into the quantum realm. In 1969, he published a paper demonstrating the possibility of producing excitons in tetracene crystal through the absorption of a single photon. Pope's research laid the foundation for a number of Nobel Prize-winning research efforts, though Pope himself never won the award. His biggest accolade was the Davy Medal, awarded by the Royal Society for outstanding contributions in the field of chemistry. Pope received the award in 2006, quote, for his pioneering work in the field of molecular semiconductors, which has now become a large and important area of semiconductor science and technology.
We shift now to something completely different. Not just different from AI supercomputing, but altogether different. You may recall we started Season 5 of All Things Photonics with a discussion on what it would take to send invertebrate organisms to space. We talked about why one would wish to do such a thing, and what could be ascertained from such a mission. Even before that, last fall, Photonics Media reported on research coming out of the Indian Institute of Science and Indian Space Research Organization. Scientists there had just published a paper introducing a peculiar, self-contained, modular device to cultivate microorganisms. The work could enable biological research in outer space. Now, 7 months later, we finally have a chance to dive into that paper with two of its authors, Kaushik Viswanathan and Alok Kumar. The team's device derives from an ambitious quest to understand microbial behavior in extreme environments. The device, in its current iteration, incorporates a photodiode sensor and an LED to track bacteria development with minimal human involvement. Kaushik Viswanathan, whose voice is the next one you'll hear, describes the beginning stages of the research. The proof of concept work was a bit more agnostic back then. While the device Viswanathan and Kumar describe as highly unusual, its optical components are really quite familiar. Viswanathan explains the motivation, as well as why the self-contained device classifies as modular.
We were trying to make a platform that basically could be put together for any biological experiment, any sort of growth measurement, activity measurement type of an experiment, which wasn't really just restricted to, say, the bacteria that Alok's lab was interested in or that people around us were interested in. So we were actually thinking of making a more general purpose biological payload platform for measuring, maybe in the long run, not just things like activity, but maybe things like fluorescence, mixing, and things like that. So the phrase modular that we put in part of the design was to make sure that we could do that. So for instance, if you look at the hierarchy that we've described in the paper, there are 3 levels. And let's say tomorrow you want to change the particular bacterial strain you're looking at. You want to make a measurement in the green end of the spectrum, for instance, right? You just have to take out the cassette and put back a new cassette, which has the corresponding sensors mounted on board. And the rest of the logic basically remains the same. So the way you mix the media, the way you do all of this other stuff, the interfacing, the communication, the onboard storage, everything is the same. So in that sense, you could pick out parts that you feel you would need to alter for a different experiment and then use that as needed.
And so the individual compartments, you use the term cassette. That's an important word here because the individual compartments of this device are called cassettes. Can you tell us what the significance is of building multiple chambers into this self-contained device? Because that would enable multiple experiments with a single device. And that means different types of experiments. And that's a pretty remarkable thing.
The word cassette is basically because it visually resembles like an old audio cassette, right? It's just a small rectangular slab. The idea of having multiple of these is to have redundancy, like in any other space experiment. So if you have 3 banks of 4 experiments each, and each one is run by its own microcontroller locally, if you have a failure, let's say in the pump that's doing the pumping, or in the microcontroller, or in one of the valves, the solenoid valves that determines how much fluid goes in and so on, that cassette is affected. The others still continue to function. So you will get data out from the experiment even if you have a component failure at the single cassette level. So that's the idea for the cassettes.
Now that you know a bit about this curious biophotonic device, you deserve to know more about what such a thing could be used for and what it might be used with. For that explanation, we turn to Alok Kumar. He literally takes us to Mars when we ask him what organisms he's studying in his lab.
The ones that we are studying, one of the benefits we see that if this bacteria, you could potentially, if you had a colony on, let's say, Mars or Moon, and you wanted a natural process by which bacteria utilize, let's say, waste, and at the same time, it leads to a good output for the colony, that would be great. So this particular microbe actually uses urea, which is present in, for example, human urine. And what it can do is it can utilize that, metabolize that, and use it to perform this biocementation process, and out comes a brick. So in a sense, it's a process which uses waste and generates something useful out of that. Now, there are multiple strains which can actually do this. We are looking into other strains also which use slightly different cycles, which can also sequester carbon dioxide. So while, let's say, when this calcium carbonate is being precipitated, the carbonate part of this calcium carbonate can come from dissolved carbon dioxide. And let's say on Mars, there's enough carbon dioxide, right? So we can potentially use that and still be able to generate some important product for ourselves. So I'd still say this is a bit futuristic, but I think this is quite interesting. The reason being, it has happened on Earth, that this bacteria is it's existed for a very, very long time. It's a very ancient process. Biocementation is used by different types of organisms. Termites use it to build their homes. Similarly, there are other organisms too. So maybe we can learn from nature, and maybe our houses on the Moon and Mars need not be that different.
That word that you heard that you likely didn't know was biocementation. Even though it happens here on this planet, we'll define it for you. It's an ecological process based on a microbial-induced carbonate precipitation, or MICP mechanism, which results in the deposition of calcium carbonate. Kumar also ended that last thought with a look ahead to mankind's residences on the Moon and Mars, and before we go there, in either a figurative or literal way, Viswanathan brings us back to Earth, in a literal and figurative way, by telling us about the optical components that comprise this analytical instrument.
The idea for this being the first experiment, the idea for this was reasonably simple. So scope was very simple in the sense that before doing activity measurements, for instance, we couldn't embark on looking at whether this type of biocementation, the kind that Alok was talking about, even happens. So before we can get to that, we wanted to see if we could just do a simple measurement of looking at how bacterial activity changes in a microgravity environment. Now, if you look at it from that point of view, the simplest thing you can do is to do an OD measurement. And the simplest way to do an OD measurement is to use an LED, a light source, and a reasonably competent photodiode. So both of these components are off the shelf. We've been working with the Indian Space Agency, and they have their own substitutes for these, which are space grade and so on. But at its heart, it's a very simple system. So the idea is you have this chamber, and the main technical challenge continues to remain in how we populate the chamber with the bacteria and start the experiment, it turns out. But let's assume you do that. The main thing you have to do is pass light through the chamber for a fixed distance, 1 centimeter, and just measure how the intensity drops as the bacterial activity starts. And we query this information over a period of, I think the paper we reported 36 to 48 hours. Could be, if you have a longer chamber, it could be a little longer than that. And we observe the standard 3 or 4 phase curve for the bacterial activity. And so that really is, at heart, it's a very simple experiment.
If you listen to the first 2 episodes of our podcast season, you'll be somewhat familiar with the notion of launching very small creatures into very faraway places. Low Earth orbit, in fact. And that very same thought is in play here, as are concepts that hit on microfluidics, metrology, and light sourcing, albeit still in a laboratory setting. The biological angle of bringing these organisms into a dormant state is where the experiment begins.
So how do you get the bacteria into a dormant state? Keep them aside for 3 months, 4 months without having them change their activity whatsoever, and then ship them off into low Earth orbit and then start the experiment remotely, right? So that, I think, was a big technical challenge. And in order to accomplish that, we used, again, a reasonably simple solution. I think it's a sequence of valves and electronically actuated solenoid valves, miniature ones, and a motor, basically a peristaltic pump to do the fluid channeling. And if you look at it, that's the main source of the power consumption. The idea of doing the simplest possible experiment just to see if it's feasible to have these bacteria in a microgravity environment and have them do their stuff as we would expect, right? That's the simplest question you can ask, I suppose, from a biological point of view. If you look at it from there, and then you look at what analogous experiments people would be doing, let's say in a lab setting with a spectrophotometer or something like that, at the end of the day, it's just a light source and a light intensity measurement, right? So if you come at it from that point of view, it is a very simple setup. The sensing setup is very simple. It's, again, stuff that most people who've dabbled in electronics are probably very familiar with. So I think the main challenge has been in trying to put this together in a self-contained package and in making it, well, reasonably, again, I don't want to jinx it like Alok has been saying, but in a reasonably, fail-safe manner. So we have enough redundancy built in, we have enough compactness built in. It's a small footprint device, it has a low power footprint and so on. So those were the primary challenges, again, with most of these space-based applications. And, in the process, I think both of us also have realized how much we can do with stuff that's already available around us, right? I mean, looked at YouTube videos where people open up an old desktop computer and just take out the most random of things that you wouldn't really expect to be there. So it's really been a bit of an eye-opener for us in that sense, I think.
And just to add to that, I mean, while the present experiment is simple in terms of the measurement of the optical density, to go from here to slightly more complicated experiments. So there's two real issues here. One is the engineering complexity and there's the biological complexity. The engineering complexity to take it a scale up is probably not that complicated because, for example, you could just incorporate filters and make it a fluorescence sensing device. But the biological complexity of getting fluorescent molecules into your organism or having the organism express those molecules as a function of some external stress, that becomes a complicated biological question or a biological engineering problem. So the moment you put these together, I think that's where the brilliant science occurs, that it's some things that the biologists are doing every day in their lab, but at the same time, you bring in this kind of a engineering solution to this together and then put this in space. I think that's where the whole interest lies, and that's where the whole game lies in the next few decades. And the biological organisms, there's so many things to study. People have been studying biofilms. People have been looking at pathogenic bacteria, oral biofilms, etc. in microgravity. Some of these are anticipated unknowns, right? We know that space will change those. But then I'm sure there are a lot of unanticipated unknowns as well, which these devices hopefully would be able to unravel when they do these experiments, specifically with different biological samples.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.